Let me now formally introduce Professor Mike Steckler from Columbia University, USA. So, Mike is a geophysicist and he works mainly on sedimentary systems with projects related to both tectonics and earthquake and sea level and stratigraphic. He did his PhD degree from MIT, Cambridge, USA in 1976. Then he went to Columbia University for his MPhil and Master's PhD degrees in 78 and 79 respectively. Then he went to the other Cambridge, the Cambridge UK, University of Cambridge for his post-doctoral research. And he has been working at the Lamont-Doherty Art Observatory since 1982. So he has been there for many years. Today, Mike will be talking about integrated observations of vertical land surface dynamics and freshwater aquifers in the coastal Ganges-Brahmaputra Delta. Our MSc students will be particularly benefited from this talk, but all others will definitely be benefited. In our Delta Process and Management class, we have referred to Mike's paper number of times. So this is an opportunity. After the lecture, you can talk to Mike about your research and other things. So with these few words, I would like to invite Professor Mike Steckler to start his presentation. Please, Mike.
Okay. Well, everyone, thank you for inviting me. I realize with this introduction that half the time since my PhD, I've been working here in Bangladesh. There are just so many interesting things going on in your country, from the tectonics to the sedimentary processes and river revulsions. And so I can only talk about part of it today. And so today I'm going to concentrate on the work that we've been doing in the coastal zone for the last 3 years. And this is work that's been collaborative with a large number of people, of which you see some of them here, and many of the Dhaka University students have also participated in this work. Okay, so, here is, your delta, and to set the stage for interpreting the results, I want to think about the changes that happen with sea level. So that we know, for instance, over the last 800,000 years, we've had a lot of very high amplitude sea level changes, and in particular, at the last sea level low stand about 20,000 years ago, the sea level was 120 meters lower than today, and the shoreline was out near the present shelf edge, and then sea level rose up. And before that, there have been multiple large amplitude 100,000 year cycles in sea level. And so that has an impact on the recent history. So to show you, this is a stratigraphic model that I've built showing the stratigraphy from this is from a very smooth sea level curve. This is a little bit easier than if I put in the actual sea level curve. And you can see the shoreline deposits are in yellow, so right now the shoreline's in here. You can see as sea level falls, the shoreline moving out, and the shelf deposits growing in front of it. Then here you can see a transgression coming back, and then progradation back. So that what has happened is sea level has risen and fallen, and the delta at times has eroded down when sea level has fallen, and then deposited again, all the while slowly growing. And you can see that this is a little piece of a seismic line collected by Burkhard Spiess and Thomas Frank from Bremen in Germany. And they actually have a cruise offshore Bangladesh starting right around now, where they're going to be collecting a lot of seismic data like this, as well as cores and other data. So what you see is a short stretch of seismic line that goes down about 1 second, roughly 1 kilometer, and this is the surface from the last low stand. And you can see here this progradation of these cliniforms going seaward, and then the transgressive, and it steps back. And before that, you can see the previous progradation. Here's another progradation. There's another progradation, and these are from the 100,000 year cycles, where they think here's where they estimate where the beach was, and so this was the beach and this was the shelf edge about 20,000 years ago, and that's all way out here, and then sea level rose back up, and the sediment increased and started creating the modern delta. But what happened during that sea level fall, when sea level was way down, is the rivers eroded very deep valleys. And so Steve Goodred has drilled now probably about 500 tube wells for stratigraphy, and you can see in this contour map the deep valleys of the Ganges, Brahmaputra, and Meghna that have cut. We don't know exactly how deep it goes because the tube wells only go down to about 90 meters. But I know that in the swatch of no ground, the Pleistocene surface here is about 500 meters below the surface. And so, this may be up to several hundred meters here. So caused by this sea level drop. We know from some of the work from the German group, so this is Louisa Palamangi, mapping the low stand shoreline was out near the shelf edge. So the shoreline was out over here, and we had deep valleys cutting in. And this is, another stratigraphic model showing at low stand, we had fluvial down to a shelf edge here, and then during the Holocene, we transgressed that with marine Holocene sediments, and now the delta is prograding back over that. That's part of why in the coastal zone, we have the coastal zone, and then we have the Holocene is saline, but I'll show you underneath that, there is fresh Pleistocene in aquifers. Okay. And of course, one of the things about the rivers is, or the delta is, I'll show you the deltas are sinking. This is that, this is sort of how I like to think about the delta. If you look at what the relative land surface is, depends on sea level, what sea level is doing. So right now, sea level is rising. The delta is sinking, but the sedimentation is important for helping it to keep pace with it. So the subsidence increases. Whoops. So the sedimentation increases the problems of relative sea level, but sedimentation counters it. And right now, the sedimentation is coming down, and is most of the sedimentation is relatively close to the river and the overbank flooding that you get. And the areas that are away from the rivers are not receiving sufficient sediment, particularly in southwestern Bangladesh, and it's even worse in coastal West Bengal, since a lot of the sediment goes down the swatch of no ground and doesn't reach West Bengal. And of course, one of the effects of that land going down is that the rivers will avulse and move around and switch to try to fill this space in because of the mismatch between the subsidence and the sedimentation. So I focused a lot on trying to understand the subsidence part. And one of the things that I've begun to realize as we've started making measurements and keep getting different rates is that we're really a lot like the blind men looking at the elephant, that, you know, every measurement we make is some relative measurement to some surface, and depending upon what measurement you're making, we're getting very different numbers. And so we really need to put them all together to try to get an understanding of the subsidence. And so we've been trying to do this for a long time. You can see how we've been aging through time while collecting data. So, you know, we've done, you know, tube wells and seismic imaging to look at things on the Holocene timescale. I've begun to look at historic sites, and some others have looked at them as well, on the order of hundreds of years. And then I've been particularly focused on some of the real-time measurements. I've been particularly using GPS or GNSS and collaborating with people for rod surface elevation tables, tide gauges. I'll show you a compaction meter we installed, and I'm starting to collaborate with people on doing INSAR. So here you can see the whole array of measurements, and one of the things is that, you know, different measurements measure to different depths. So I've done a lot of GNSS on buildings. I'm going to be heading from here down south to service some of those stations. And of course, the buildings are built on foundations or pilings, and so they don't measure anything that's happening near the surface. Where the rod surface elevation tables make measurements but relative to the base of the rod, which is only 24 meters. And so these are a lot of complementary measurements, and I will, you know, and so this is the array that we're hoping to start doing over the next few years, and I'm going to concentrate on some of these and show you some of the results, and then try to synthesize them. So here are some of the tube wells that Steve Goodred has drilled, and Celine Grau has looked at those sedimentary record and the radiocarbon dates and tried to separate the subsidence versus the sedimentation effects. You know, because if a river comes and erodes down the sediments and deposits fresher sediments, it looks like you have a very high subsidence rate, but that's just filling in the hole. That's not actually subsidence. So she separated them, and what she sees is from the hinge zone, we see very little subsidence, and then as you go seaward, it increases to about 4.5 millimeters a year. One of the things we managed to do in 2011 was we went on the Kokomoni, a Sundarban boat, and we traveled throughout the rivers of Bangladesh and did some very, very high resolution seismics. We had a 50-meter, 48-channel streamer and a little tiny GI gun. And you can see the track here from the north to the south. And so we're only imaging down maybe a couple of hundred meters at most. And you can see this strong reflector we picked up. That reflector is the base of the Brahmaputra Valley during the glacial low stand. So you can see it here. But if you look seaward, what you see is, but if you look seaward, you can see that reflector starts dipping seaward. Now, rivers don't steepen as they go towards the coast. You know, the river should be straight or flat. So this is actually showing some of the subsidence in the coastal place, and it starts right at the hinge zone, and we start seeing the subsidence increasing to a couple of millimeters millimeters per year at the confluence with the Brahmaputra. And you can see here's the seismic key of both piece and 2-inch length. Okay, and this is Mahmoud Sakar from CGIS has looked at some historic sites and tried to measure, subsidence, and he's getting, fairly modest rates of subsidence. And, I was really curious because the Shakya temple in the Sundarbans has basically 0 subsidence. And we went back. Here is the temple. We had to get there through boats and hiking through the Sundarbans. I've been told that they've built a better route for tourists to come visit the site. And the important thing is for this is the plinth level, that you will build up the ground surface above the flood level for a plinth, and then build the structure. And what Mami and Tucker did was estimated that the plinth level was at the entrance to the temple. But I think her problem is that this is a Hindu temple to the goddess Kali, and while mosques are communal prayer groups with then a level entrance to the ground, temples are the homes of gods and goddesses, and they're often to have a raised entrance. And so we think this ridge at the base is actually the plinth level down here. Yeah, and then Steve Goodred and Diman Mondal court around there, and 1.5 meters down, they found a brick layer that we think is the base of where they built up from the land surface. And so if you look at my estimate of a revised plinth level that's lower, and their depth of the brick layer, you end up with about 3.5 millimeters a year of subsidence at this site. For instance, Chilhanabooth has worked with some of the salt kilns. This is the one at Katka. This one has been washed away now. They were buried and then uncovered during Sidr. And when we went there, so you would, for the salt production, you would have a salt pan near the spring tide, high tide, so that it gets flooded during the spring high tide and then evaporates for 2 weeks. And then you've got salt kilns, which would be a little bit higher so they stay dry, to take the brine after 2 weeks and fire it to make salt. Here we are at, we are standing actually at this salt kiln, and by the time we finished drilling, the water was above our knees. So this is clearly no longer at spring high tide level. And Chilhanabooth estimated about 4.1 millimeters a year of subsidence. And since then, they've gone out and found actually about 100 more of these salt kiln sites all along the coast. Some of them dating back. This one is about 300 years old. Some of them date back to up to 1,000 years old. Okay, and then we installed a direct meter to measure compaction. So we drilled wells from 20 to 300 meters deep, and we installed optical fiber, so the same thing that's used in communication. And so these are the monuments that we built, and then we cemented the thing into the bottom so that the fiber goes down, makes a U-turn, and comes back, so that the 4 fibers make 2 pairs. And then we use an electronic distance meter to measure the length of the fiber every week. And here, for instance, is one of the measurements for the 40-meter well, where there's a big seasonal signal, but overall you can see that the fiber is shortening, in this case, about 5.6 millimeters a year. And if we plot these dark blue symbols are the rate of shortening that we're seeing versus the depth that the fiber is anchored to. So the deeper we go, the more subsidence we see, and we can see this forms a nice curve suggesting about 9 millimeters a year of subsidence. But over here, not showing, is the Holocene-Pleistocene boundary, and what you see from these two sides is that basically there is no subsidence, no compaction going on within the Pleistocene. We're seeing all of that compaction happening in the Holocene. And part of that is that when this area was eroded down, the sediments underneath, when they get exposed, they don't uncompact. And they don't, and then until the weight of sediment above them exceeds the maximum that it's seen before, it doesn't start compacting again. So as a result, in the areas that have been heavily eroded, there is no compaction going on in the Pleistocene and deeper. The compaction is happening within the Holocene. Yeah, unfortunately, this site was built by a river that had been really wide and then narrowed to the point where you could sail on it in high tide, but at low tide it was about 6 inches of water. You can see this big bridge that was built for when it was wider, and then the BWDB came by and dredged it to make that river wider, and as a result, our instruments collapsed into the river. And so, look, we got 4 years of data, enough to make good estimates, but the instrument is no more. And then my focus has been a lot on GPS or GNSS. So here you can see this is at pole 32, an antenna, and that would be, powered by a solar panel. Here's Santa Cinca, and where we have a receiver and batteries inside a case to power them, and all this data was processed by Bar Oyan. And so what happens is we take each day's results and process it for a position, and that position is in 3D. And so we do it in north, east, and vertical. And then you can see that this antenna is moving to the north and east, and that's due to the overall motion of the Indian plate to the northeast. So if you fit it with a seasonal signal, you can see we're moving to the north and east together. They combine for about 5.3 centimeters a year to the northeast, but you can see the site is going down at about 5 millimeters a year. And then Carol Wilson has been doing the rod surface elevation tables that I mentioned. So where you push a rod down to the depth of refusal, or 80 feet, and then in the end it looks like this. And when you want to take a measurement, so this is what it looks like. And then when you want to take a measurement, you attach this arm on. Here you can see she's on a board so she doesn't touch the ground around the monument, and attaches that, and then carefully measures the elevation with these 9 rods, and they move this around to 8 different positions and get 72 measurements of elevation. They also put down sediment tiles flush with the surface to then measure the sediment accumulation, and then they remonitor that every 6 months to get the elevation change, sediment accretion, and the difference between those is the shallow subsidence. So if you've accumulated 2 centimeters of sediment, but the elevation only changed by 1 centimeter, that means that you had 1 centimeter of compaction between the surface and the base of the rock. So it's only measuring to the base of the rock. And I have one site where we've put a GPS next to an RSET so we can see how the rod is moving. Okay, and this has just a little hole so this rod can move up and down, and it's separate from that brace. And so here's what that synthesis looks like. Here's swing Browns number and also some numbers from tide gauges. But if we take a look at the rates, and what I've done here is the font size is proportional to how long the instruments have been in the ground. So the instruments that we put in 2019 are in a very small font because it's not been a long enough time. Whereas, for instance, in Kulna, that was installed in 2003, so we've had a much longer time and more accurate measurements. And what you see is in the eastern part here, we have basically 4 millimeters a year, and the historic sites are also 4 and 3.5. Those are fairly similar to what we see on the long-term rates. If we look farther west at Kulna and Boulder 32, we see more like 5, and at Huron Point, we see 7. And so we're seeing a few millimeters a year higher, and we initially think that that's because the sediments are muddier farther from the river mouth, and they are showing more compaction. But what concerned us was the compaction meter and that RSET are showing 9 and 10 millimeters a year. So, I mean, those are shallower, they don't even include the deep compaction, but yet they're showing a higher rate. Right? So, if you look over 32, the archaeological sites are showing one rate, the GNSS is showing a slightly higher rate, and then the RSETs are showing a much higher rate. And so try to understand this difference with depth, we went out and resurveyed a bunch of geodetic monuments from the survey of Bangladesh. And so they have a whole lot of monuments that were installed in 2002 and never remeasured. This is the one at Huron Point, which is nicely painted. That's not what most of them look like. Here is remeasured one. This is more what they tend to look like. So we set up a GPS tripod and carefully measured our elevation above the mark and recorded for 24 to, in some cases, 5 or 6 days. And you can see this gives us we tried to get to 55 sites. We successfully got 48 sites. That this picture is from this one to look at what this substance was. And this is what we got was a mixture of rates. From the red ones are very low, less than 5 millimeters a year. Many of them we're seeing 10 to 15 millimeters a year, and then scattered throughout, there's a bunch of rates that are higher than 20 that we were very suspicious of. And because you can see without those blue rates, we tend to see much more of a smooth pattern of lower rates in the northwest and higher rates in the southeast. And this is what a cross-section looks like. And our initial interpretation, what happened to, this is lost, oh no, there it is. So there should be a line across like this over here where we see very little subsidence in the northwest, and then we go up to around 12 to 15 millimeters a year here, and then we're a little bit suspicious of those down there. But you can see the continuous GPS gives us one rate, the RSET and compaction meter gives us a higher rate, and then the campaign GPS sites gave us a still higher rate. And so for this, we remeasured these 4 ones that are marked over here, So this was the first site. This was site we found the site buried because they built a new school building and dumped the soil from the excavation on top. But one of the local people helped us find it. And what you see is here's its position back in 2002. Here's the position when we remeasured it in 2020. And then Hasnat Jaman went back out in October and remeasured it. And you can see we got 3 measurements in a straight line. And that was true of both of the sites that had the 13, 14 millimeters a year. When we went to this site that had 25 millimeters a year, here's the initial measurement, here's where we remeasured, and then in October it had moved higher. And we think that high rate is because this site was initially installed up at the road level, and we saw some others where they were up at the road level, and then it slumped down. And now it's slumped down into this field, and now it's moving up and down seasonally with that field. So in October, it was at higher elevation. And so we think that we can throw out those higher rates for now. It's possible some of those in the Sundarbans might be true higher rates. I hope in the future to go out and remeasure these once again to try to better understand the differences. Yeah, so, you know, and one of the things that we see in this rate increasing as we go seaward is this is from the tube wells showing the amount of muds. And so you can see a transect G is mostly sand, but the transects that are closer to the coast are mostly muddier. And you can see here in this section that we go from very sandy in northwestern Bangladesh to very muddy as we go across, and this is where the GPS is going. So we get sandier sediments in this northwest corner and muddier sediments as we go to the coast. But we also took a look at that Holocene thickness that we have. And so here are those paleo valleys I showed you, and this has been mapped out that in between the paleo valleys where the land was exposed and weathered, it formed a clay layer called the LGM paleosol, which is also very important for separating the high arsenic Holocene from the low arsenic Pleistocene. But over here, we also see that all 5 of our sites with very low rates were on top of this LGM paleosol where the Holocene was relatively thin, and all the rates that were higher were where we see a very thick Holocene. So here's a plot of subsidence rate against the thickness of the Holocene. And of course, for these points here, we only know it's deeper than 90 meters the depth of the tube well, but it could be up to a couple of 100 meters in some of these places. And you can see we go from very sandy, thin deposits to muddier, thicker deposits as the rate changes. Now, we can't yet separate whether it's the thickness or the lithology that's most important. That's something we're hoping to do more measurements and start augering and more drill holes right at the sites to try and refine that. And so here's what that synthesis looks like. So that on our buildings, we only measure the subsidence below the foundation. At the RSETs, we only measure the subsidence above some depth. But the geodetic monuments are only about 1 meter. And so they get the higher rate because they are getting a very shallow subsidence as well as a deeper subsidence. And so if we take a look at these different measurements, we can separate out that we think there's about 2 or 3 millimeters of very deep subsidence, which is consistent with models of just the weight of the sediments isostatically depressing the land. Very little in the intervening depth, and and then quite a bit in the near surface. And in the near surface, what we realize, and we're not quite sure what that depth of near surface is, it might be 5 meters, that you have a lot of roots from the grasses and rice and trees. You also have a lot of burrows, and all of those are taking up some of the space. There's also a lot of organic matter, and then when that gets buried, you lose the roots, you lose the burrows, you lose the organic matter, and that sediment takes up a much smaller volume, and that corresponds to this 5 to 7 millimeters of compaction that's taking place in those upper meters. So we're beginning to form a view of what's controlling the subsidence, and we hope to then apply a lot of those methods that I showed earlier. It also means that the subsidence rates can be very local, so that our historic sites, we see lower rates because they don't have any of this near surface effect. On the buildings and on boulders, there's some kind of foundation, and so they don't see the very shallow. But in the rice fields, especially where there's active sedimentation that's driving the sediments down, we expect to see very high rates. So we could have higher and lower rates even next to each other, depending on the setting. Particularly, by the channels, you see sedimentary deposits that should have high subsidence rates. Within the boulders that are not receiving sedimentation, the rate should be lower. And so we're hoping to start differentiating all these areas to take a look at them, and having to work at a very small scale. So like you can't use like an instar image with a 100-meter pixel, because then you're including many different rates of subsidence within that. And so we need to scale down and look in detail to understand it and make sure that these numbers are actually correct. And in the future, we're hoping to model some of that. So I know, for instance, Ton Huytink in the Netherlands and Wageningen is doing Delft 3D modeling. We'll collaborate with Austin Chadwick, who's my postdoc, who's here in the audience, is working on modeling this sediment compaction and developing a quantitative math model. And Joe Grau is modeling that deep glacial isostatic adjustment to the sediment load. And so here's a summary of his model of looking at the layers and being taking into account the different lithologies and the weight of the sediments and the porosity to try to calculate what the subsidence is to whatever depth our different measurement is rooted to, and try to match all of them at once. And so, as I said, in the future, we hope to expand to additional GPS and RSET sites, to using INSAR, more archaeological sites, drone LiDAR, and we're using, there's a satellite DEM that we've just started producing. This is just around Mangla, to get a more detailed elevation map where we can see the fields versus the villages with specific elevations. Yeah, for instance, this is one archaeological site in the Sundarbans that's only visible at low tide. So it's clearly not at its original elevation, but there's no dating and no elevation measurements on it yet, and we hope to do that. Skip this, and just mention these slides are a bit complicated, but worrying about the future of Bangladesh in terms of the sediment supply is Jessica Rock and Steve Goodred worked and looked at, from all those tube wells and mapping out where the sediments were deposited over time. They're able to take a look and see that in the early Holocene, the sedimentation rate was probably at least double what it is today. And that was a time when there was a stronger monsoon, where things were wetter. And what we see is when the monsoon was stronger, there was more sediment coming down. And so using that to calibrate models of the future climate where the monsoon might get stronger, what they estimate is, with future sea level rise, that as the monsoon gets stronger, there will be a stronger, as climate changes and the monsoon gets stronger, there will be more sediments eroded from upstream, and that will help Bangladesh keep pace. And so you can see that the amount of sediments we needed, so without dams, will pretty close to keep pace. Maybe towards the end of the century, you might begin to erode low. But the big problem is India and China are planning all kinds of dams and the river interlink project. And if those happen, then that will greatly decrease the amount of sediments available to Bangladesh. So right now, Bangladesh hopefully has enough sediments coming down, but of course, as I mentioned in the beginning, it's not distributed where you necessarily want it. So land is growing near the Meghna River mouth, but we're losing land in the southwest because the rivers aren't there anymore. Okay. And then the final piece of my talk is I want to talk about a survey that we did now almost 2 years ago. So we went on the Kokomoni boat, and we went down the Pusor and the Tatulia channel doing electromagnetics, mostly magnetotellurics, which is, and I'll show you the results from the Pusor River profile. So what we use, so the magnetotelluric method is we put out magnetometers in the east-west, north-south, and vertical directions to measure the magnetic field, and we put out electrodes that span 100 meters apart to measure the electric field. And the magnetotelluric signal is the electromagnetic waves coming from the solar wind that penetrate the ground, and depending upon the resistivity of the ground, you get a different signal back. You know, where the electric field penetrating produces a magnetic field and vice versa. We also did a little bit of transient electromagnetic where we have an active source of pumping electromagnetic energy down and then recording it. But I'll talk mainly about the magnetotelluric. And the importance is that fresh water and salt water have very different conductivities. Fresh water is very resistant, whereas salt water is very conductive. And so here you can see, so fresh water has a high resistivity, and saline water is more conductive, low resistivity. And so we went around to the Sundarbans. These are the magnetometers. They're about 1 meter long. It's carrying the equipment through the fields. This is when we hit low tide at the Sundarbans. Here you can see Nafi Suzi spooling out the wire 50 meters for the electrodes. And here we are setting up. Here's Hui. We process the data. When we were in the Sundarbans, we had to be careful. You couldn't allow one person to go off on their own. We had to do it in groups of 4s, preferably with one of the guys with the rifles, and make lots of noise to keep the tigers away. And Masood can tell you, we saw lots of tiger footprints. No tigers, but we saw lots of footprints. And so this is what the results look like. I'm not going to go through all the complicated processing, but in this map, this goes from the north is around Khulna, the south is Dubla Char, near the coast. Blue is saline, red is fresh. And so what you see in the shallow part, for instance, near the coast at Dubla Char, you see essentially seawater. And you can see, and this is, so this is 2 kilometers in scale. So this is sort of 100 meter Holocene thickness. You see saline moving towards becoming brackish as you approach Khulna. But underneath it, you can see these two bodies of fresh water. So below Puma, you can see this is very fresh and clearly drinkable, and it's about, goes down to about 500 meters depth, so it's about 400 meters aquifer of fresh water. In the Sundarbans, we see another aquifer. It's a bit more brackish. It does in the center get to be low enough to be drinkable, but in between we see this saline gap where there is no fresh water. And at first we were very confused, and then we went back to this map that we saw and realized, and so here if I take a line sort of along the maximum freshness in here, you can see the northern red, the southern sort of orange, and that gap corresponds to where the Ganges Paleo Valley cuts through our profile. So that saline gap is actually coming in and out of the page. And what happened is we don't know how deep it is. We know this is 100 meters. It could be 200 meters deep in here, extending down like this. And so during sea level low stand, this was a deep valley, and we have the hills. And then when sea level rose, that became a big marine estuary and brought saline water. And of course, up here, we have that LGM paleosol that helps protect this northern water body because it's relatively impermeable. We don't have that probably in the southern one, and so there's probably somewhat more mixing. But over here, we not only have that, but we have a deep channel that was filled with initially saline water and then saline sediments. And so that means, along this zone, we probably don't have access to deep fresh water, but on this side we do, and probably on this side in West Bengal we do. This smaller zone is probably connected into West Bengal. All right, and so now with looking at the subsidence and the salinity and the way the stratigraphy was built, we're beginning to understand the patterns of subsidence and fresh and saline water, and where we can find them to keep this delta more sustainable. Thank you.
Please identify yourself and then ask your question.
So I am Shailesh. I am working as a lecturer of Department of Disaster Science and Climate Resilience. At first, I'd like to thank the organizers for arranging such a wonderful seminar, and it's really a great honor to hear from you sitting in front of you, Professor. Basically, my research interest is related to the satellite geodesy and detecting the ground deformation and motions. I have worked with detecting the land subsidence in the southeastern part of Ganges-Brahmaputra delta using the INSAT technique, as well as analyzing the spatial variance of land subsidence variations. What I have found significant spatial variations, and the land subsidence ranges from 2 or 3 millimeters to nearly 18 or 17 millimeters per year, which has a very high spatial difference for the study work. And now I am planning to analyzing the variations with the anthropogenic factors and the groundwater level or the water level and other things basically. And I know that the net subsidence is very complex because sedimentation is still going on, the compaction and consolidation rates are different, the local geology are different, and decomposition and other factors, they all are different. At the same time, performing inside has also some issues in that part, the southeastern part of Bangladesh, because the vegetation causes significant low points values and other things, which is very complex. So I want some of your suggestions on performing inside in that part, especially in the southeastern part of Bangladesh, because there's a lot of vegetations and other factors.
In the southeastern part here.
Yeah. That's the point. And another thing that numbers of INSAR technique is available, persistent scatters, time series INSAR, differential INSAR, SBS. So I have performed the time series, but I want to know that which one is more acceptable for this zone making.
Right, so I'm not an expert in INSAR, but I actually have a postdoc who will be coming here next month to join me, who's doing INSAR in the fold belt, which includes the southeast. And so she's just getting the data, and I have some colleagues in New Mexico who have used the ALLO satellite to look at it. They've been mainly looking for the tectonic signal, and it's, the INSAR is very complex because there's a lot of tree cover and vegetation that makes it, difficult. Plus there's lots of issues with the ionosphere that need to be corrected. So, we're not quite there yet. Same thing, I have a colleague doing INSAR over the delta part, and I'm not yet ready to believe the values, as to whether all the corrections have done right. That, it reminds me of like a number of years ago when processing the GPS, everybody did it a little, very differently, had their own schemes of processing, and now it's become a bit more uniform and reliable. And I think INSAR is still getting to that. It's easy to do INSAR on an earthquake when you've got meters of motion over seconds, but when you're looking at millimeters per year, it is different. The things we're interested in is what is the tectonic motions in there? Are some of the anticlinal structures actively moving and deforming or not? We have from other data, we think in St. Martin's Island is actively uplifting and deforming, and we have some hints that some of the other anticlines are in a paper that we just was just submitted. But it's still something that's in progress, and I hope, if I come back here in about 2 years, I'll be able to have much more solid results on what the INSAR says for this area.
Thank you so much. I have told that it's a great honor for me to hear from you, and it will encourage me for my future work. Thank you so much.
Thank you, Mike, for the nice presentation. I was just wondering, you showed me the cyclic component in vertical compaction measurement, and also cyclicity in the vertical GPS data.
Mm-hmm.
So what could be the possible reason of this cyclicity in this
Of the
compaction
cyclicity?
and expansion?
Oh, okay. It's actually seasonal, so we modeled that is the GPS in the buildings mostly sees is the weight of the water load during the monsoon. So we see up to 5-6 centimeters of seasonal vertical motion, where, during the monsoon, you refill the aquifers and produce flooding, and our estimate is about 100 billion tons of water, spend their summer in Bangladesh, and that can produce that vertical motion. There's also an effect of that. There's a poroelastic effect, which is the opposite direction, is that as the water table rises, the sediments expand with the increased pore water. The GPS on the buildings mainly see that loading. Our compaction meter mainly sees the opposite. It expanded in the summer and went down in the winter. And the INSAR sees something in between that's a combination.
Thank you very much.
Thank you for your very nice presentation. It's always been a pleasure to listen to you. I had also many chances to have some field work with you in the Salate area, if you remember. So yeah, this is obviously an excellent work. So you have shown the subsidence in the coastal region of Bangladesh. So as I understand that all are caused by the natural processes, right? So my question is, have you considered any kind of like subsidence related to groundwater abstraction that's been recently discussed, and how severe is the influence?
Thank you, Sanjida. I was going to ask the same question. Thank you.
Where we particularly see it is right here in Dhaka. So here you can see the GPS rates we have, and they range from 10 to 13 millimeters a year of subsidence. And we think that is mainly from groundwater abstraction. And it's very much, concentrated. In the coastal zone, because the shallow groundwater is saline, there is not abstraction going on. We don't have many in the northwest where there may be more abstraction, but we very clearly see in Dhaka, and Lamont and I have talked about trying to expand the number of stations monitoring that subsidence in Dhaka.
Yeah, but there is distinct difference in geological setting of Dhaka and the coastal area. So that might have an influence as well on the subsidence.
Yeah.
And in terms of groundwater abstraction, so there is no groundwater abstraction surrounding the Sundarban area,
Right.
but in Borishal, Patuakhali region, there is groundwater
There is
abstraction.
some, yeah.
There is significant amount of abstraction. Also in Khulna, there is significant amount of groundwater abstraction.
Okay.
Yeah, because so just if you consider the Sundarban and its fringe area, there is no groundwater abstraction. But all other parts of the southwest Bangladesh,
Yeah.
there is deep groundwater abstraction.
Okay.
So I think
Is there down in here?
Yeah.
Yeah, because, when I've been there, I haven't seen much crop growing in the.
Well, it's not for irrigation, so mostly for drinking.
For drinking water, but
Yeah,
drinking water is
so
much less.
That's
than
right.
for
So
irrigation.
there is significant difference in terms of
Yeah.
volume of abstraction, but in Khulna area, there is significant abstraction, particularly for Khulna city.
Yeah. And that's something that needs to be considered, is how much substance is coming from that abstraction.
So maybe one way will be to look into the irrigation coverage and then try to link that with the different rate of subsidence that you have seen.
So we may need to, at these sites, look at what the abstraction rates are and try to include that into the modeling.
Exactly. That will give another kind of filter.
Yeah.
Actually, in the central and southwestern part nowadays, groundwater abstraction has been considered as a factor further aggravating the subsidence in that region. So there are several works on that.
Is there any tectonics involvement?
Any what?
Any
Tectonic?
tectonics aspect? Just to know about, is there any involvement of tectonics?
Yeah. In the east, so, this is where I've mapped the deformation front. So east of here is where there is mostly tectonic. There could be a little bit of extra subsidence in front of that from the foreland deformation. But this is mostly an area past where there's much tectonic influence. But, in these areas, I'll be visiting a site, for instance, is on top of the Lamont anticline or around Siddhakun. We think most of the vertical motion we're seeing is from the tectonics, and that's why I didn't talk about those today.
And you have drawn a line of the deformation part.
Yes.
And the subduction starts before that.
I think that's about where the subduction starts. This is basically the line where I start seeing anticlines in the subsurface.
Yes.
So there's anticlines in Bola, there's the constant field, there's plenty of folds and gas fields in here. And so I'm considering all of that tectonics. If I get more information that pushes it farther, I can move it around.
What about Indian plate subduction? Where did it start? Bending of Indian plates.
Yeah, I think this is basically where it starts, and over here, all the folds
Before
are from,
what line?
what?
Before what line?
Before,
Information part. Subduction should start before that.
no, it starts, I think, at there. The mega thrust is buried and extends about up to here as far as we can tell.
Detachment plate I talk about. Detachment.
Yeah, and then it's very shallow across here, and then it deepens farther.
Bending should start
farther east.
somewhere along this line. Bending of plate.
Yeah, that's where it starts, but it's very little bending at that point.
But it should start before that part line, yeah, before the part.
Yeah, I've done some models, and there's a little bit of substance that you would get in front of it before the tectonics due to the flexure. It turns out when you do the model, because the accretionary wedge is so broad and shallow, most of the adjustment is directly underneath it and doesn't extend very much in front of it.
Now there is a controversy. Do we draw information part line through data and it ends at edaphic part? So there is a controversy that there should not be this line. Properly it is not drawn.
Okay, maybe we can discuss that later.
Yeah, I think it will be better if we discuss this later on. Anwar should be.
Thank you very much, Mike. It was a very nice presentation. Thank you. So what I understand that most of the Ganges River shifted to the present position, and estuary position also shifted towards east. So what do you think? How much this shifting of the estuary or the coast of Ganges related to tectonics or sea level rise actually, or delta development processes?
This is, always a question, because the rivers are always moving around, and in fact, Austin has worked on how sea level rise can affect the rate at which rivers avulse and shift, and the tectonics can too, by producing lateral tilting. So we think, like for the Brahmaputra, shifting between the Jamuna and Old Brahmaputra is probably affected by the tectonics of the subsidence of Ceylon in terms of going back and forth. And the Ganges is also moving back and forth. And so, the fact that the Meghna is right around the deformation front, where, you perhaps expect a maximum of the subsidence, is not surprising. Because as you get differential subsidence, the river has to spend more time where it's subsiding to fill it with sediments than other times. And so, it will move around and will be interested by the tilt rates. But my estimates are that the tilt rates across here are very modest. They're not nearly as high as what you see in Ceylon.
To the salinity part of your talk, which has some interesting aspects. So you have not interpreted the second line yet, the Tetulia.
No, it should be this coming year. So after he finishes writing, submitting the paper on the first line, and he has another paper to write, and so probably hopefully this summer.
So there are two things. So there is evidence of this deep Ganges Valley and no fresh groundwater there. So something similar can happen in the other major estuaries as well.
Right, and I think things can get a little more complicated, because here we do have some influence of tectonics. We have the Meghna Valley, and I think we may see a more complex result in the east, and I'm really curious to see it.
But we have some evidence from the Hatia, Shondi, Basanchor in this area.
Mhm.
So there is fresh groundwater
Yes,
to a depth of 300 meters.
yes.
So I think this section will be interesting. Do you think this EM technique can be applied for the whole coastal region of Bangladesh?
You know, I think it can.
So in terms of cost, like there was a discussion about doing aeromagnetic. So compared to aeromagnetic, I think this is going to be a lot cheaper.
I mean, the aeromagnetics, I think, is more limited in what kind of depth it can get to, or the EM. You know,
Aero EM, okay.
you can't get deep enough. You know, this is not a cheap method. You know, certainly in the marine areas, you can work very easily. You know, for instance, the data in here is going to be noisier because there's more population and power lines. You know, the data in the Sundarbans is very, very clean because, you know, tigers don't use electricity.
So this is interesting, the freshwater lands underneath the Sundarban. So, up to an exploration depth of 300 meters, we did not find any freshwater yet
Okay.
surrounding the Sundarban
In the
area.
Sundarbans, again, it's going to depend where you go, you know, in terms of where those deep valleys.
Another issue is like the clay thickness is very high compared to the other parts. The superficial clay thickness is very high.
Yeah, and it would be really good to, you know, combine
All this information.
you know, the data from wells with the EM to try to get a better spatial map. We just have a profile.
Okay. No, I think that will be very useful. Use the microphone.
If there is a letter, switch on. Hello? Hello?
Okay, thank you. So if there is a lateral shifting of the estuary or Ganges river system towards east, so there will be a gradual shifting of the saline water intrusion zone with time.
Yeah.
So in the Sundarban area, it was more uninterrupted, I guess. Little bit more uninterrupted. In the eastern part, there will be some gradual shifting and then saline water intrusion with the.
Yeah, I think also this nature of sediments, because Sundarban might have been like, it has very thick clay in some parts, like up to 300 meters, there was no aquifer found. So in some of the areas, the clay thickness is very high. So there could be like differences in terms of the depositional environment, depending on the presence of the paleo river and the incision of the valley.
Yes.
So there, I think this is a good way to look at it. So the other line, interpretation of the other line would help better. And then if we can do more lines, then I think we'll have.
Right, so, you know, we see the saline water here, but, you know, as we go this way, you know, if you were in the eastern part of the Sundarbans, this may not extend that far, but it may extend more in the western Sundarbans.
Yeah, but the physical evidence that we have, that if you go to the other side of the Baleshwar river, apart from Patharghata, there is fresh groundwater. But on this side,
Right,
yeah,
there's fresh groundwater except right in here.
Yeah.
Yeah, which, you know, could be the Brahmaputra paleo valley, and over here is fresh groundwater.
This
Yeah,
is-
so, right, and hopefully we'll image that as we come through.
Sir, local people in the rural area are abstracting water from this freshwater zone? This freshwater? Why?
Yeah, this
why?
one. That's right. The
Currently-
one on the left, not the one in the Sundarban area.
Yeah, this one. left
No,
one.
this one is
That
not.
yeah.
Not yet.
Well, in the Sundarbans, it's the middle of the Sundarbans, they're, you know,
Somewhere. So the underneath Khulna city, you know, all this area they are collecting water.
I
Okay.
have one last question. what would be the scenario in the next 50 or 100 years in this area with respect to subsidence and CO2?
You know,
I think you have mentioned that if the current rate of sedimentation is not interrupted, then we are good until 2080.
yeah, well, but,
So
you know,
most
except-
people sitting in this room will not
Yes,
survive after that
except,
time.
you know, you're good to 2080 for the overall balance, but there's more of the sediment is here and less of it is here. And over here, the polders don't let the sediment
Sediment
into where
come.
the people are actually living.
So we'll have to demolish all the
Is
boulders.
there a problem of starvation of sediments from upstream? Because number of dams are.
Yeah, that's he already mentioned that.
Right, that I think is the biggest risk.
Even somebody modeled a 50% reduction of sediments.
Yes, no, arena
So that would
overrate,
be a
yes.
problem for us.
That would be a very big problem. I think that's the biggest problem. The dam that worries me the most is the Chinese have proposed basically a tunnel around Namche Bawa, and that's the area that produces 50% of the sediment in the Brahmaputra. You know,
Till now,
so,
there is no problem.
what?
Till now, there is no problem of supply and balance of this.
And when people make arguments about building that dam system for power, they say, see, we're not taking any of the water, but they don't think about the sediments.
What about this folder system, 139 folders? But within the folder, there is a difference of 1 meter.
Yes,
So it is creating a lot of problems, water logging and
it
excess sedimentation.
it is a clear problem in the polders, because the polders are going
This is a
to,
man-made disaster.
it's absolutely a man-made disaster. And once you build them, it's very hard to unbuild them.
Even now we are starting TRM, tidal river
Yes.
management. That is not effective.
It's not,
Effective.
yeah, that's,
So what is the solution?
I'm not sure. Right now, the government is building bigger polders, is building bigger embankments.
Okay.
We have to create another one.
Yeah,
Yeah.
we can continue this discussion. Like, thank you, the students and guests and colleagues for attending this seminar. So Mike will be here this afternoon. So if the students would like to talk to him further, so he will be mostly with Professor Amarushan Bhuya for this afternoon, and then you can come and talk to him. Thank you very much for listening to this seminar. I've seen a lot of first year students. You may find this difficult now, but when you come, you become little senior, third year and fourth year and masters, then you will understand this significance of this seminar. Okay. So the good news that Mike shared with us that until 2018, we are 2080, we are okay with the current supply of sediments. More than 50 years now, but there are risks. Dam is going to be the major issue. So we are impacting the nature with our activities, anthropogenic activities. In the future, we have to be very careful about this. So how to manage this river system, how to manage this coastal system, we have to be very careful about it. So with these few words, thank you very much, Mike, for this presentation. Thank you. So guests from different organizations, please join us at the chairman's office.